So manganese has how many electrons when it's neutral? 25. Is that right? Can someone give me the electron configuration of manganese? Who wants to do that? Yes, DJ. What is the electron configuration of manganese?
1s2,
1s2,
2s2,
2s2,
2p6,
2p6, 3s2, 3p6, 4s2,
and
3d5. All right. Now, so you have your periodic table. Is that right? Now, in your periodic table, how many electrons can go into the s orbital? 2. An orbital, we cannot draw orbitals like this every time. Is that right? It's going to be very difficult. Instead, how do we show orbitals? We show them with a box. Are you with me? And how many maximum electrons can go into an orbital? 2. So the idea is that one spins clockwise and the other spins counterclockwise. Is that right? And so how do we show that in an orbital diagram? An up arrow means it's spinning clockwise. Alright? Whereas a down arrow means it's spinning counterclockwise. So if there are 2 electrons in S, how many boxes will you draw for S? Only 1. What is the maximum number of electrons that can go into P? 6. So how many boxes do you think you should draw if you can put 2 per box? 3. So you draw 3 boxes if you're in the p orbital. What about a d orbital? How many you think? 10 is the maximum, so the number of orbitals will be 5. Are we good? And for f orbital, it's going to be 7. Is that right? 1, 2, 3, 4, 5, 6, 7. Is that right? So orbital diagram, as the word says, is boxes and arrows. So we know that when we look at energy levels, we looked at a picture of it last class. Do you remember that? Do you remember this picture? Do you remember 1s is the least in energy, followed by 2s, followed by 2p. But look at the 3p orbitals. They are equal in energy. Is that right? So, when you start filling in the orbitals, you have to remember that. Now, for a lack of space, you can even draw it horizontally instead of stacking it vertically. Does that make sense? You have to remember that for 1s, you have to draw how many boxes? 1. And you will put an up arrow and a down arrow. Does that make sense? For 2s, again it's an s orbital. So how many arrows will you draw? 2. Is that right? Now this is a p orbital. How many boxes will I draw? 3. And remember, all 3 of them are equal in energy. When it's an equal energy orbital, try to understand this. So P is like Px, is that right? Px, Py, and this is Pz. Now electrons repel each other. They do not like to be in the same region of space. They are forced to enter a low energy orbital. Is that right? But if given a choice with equal energy orbitals, how will the electrons occupy them? 1 in each. But then there are 6. So now it's forced to double up. Does that make sense? In S, S is lower in energy. It has to double up. Yes or no? In P, there are 3 orbitals. It will be forced to double up because there are 6. Is that right? Then comes 4s. It will double up there also. The next energy level is D. How many boxes do we draw for D? 5. 1, 2, 3, 4, 5. Is that right? And there are 5 different electrons. So how will you show them in the d orbital. Do we understand how orbital diagrams are drawn? So they ask you for an orbital diagram, write the electron configuration, and then draw the boxes and arrows. Yes?
So if you're like only doing the first arrow is pointing up in the center.
Yeah, the first you assume is the clockwise, and the second one is the counterclockwise. Are we good with that? Do you want me to do another example, or shall I move on? Shall I move on? All right. Another example?
Yes.
Which one? Which one in your packet? Let's do that page, I mean, phosphorus. Let's do phosphorus. Phosphorus's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. Correct? How many boxes will I draw for S? 1. It contains 2 electrons, up and down. How many boxes will I draw for 2s? 1, up and down. How many will I draw for 2p? 3. And it's completely filled. Is that right? Then comes 3s. So how many will I draw? 1. Then comes 3p. So 1, 2, 3. If it had been silicon, this box would be empty. Is that right? If it had been not phosphorus, if it had been silicon, this would be 3p2, which means this box will be empty. Does that make sense? 1, 1. Does it make sense? If you draw a P box like this, and if you put arrows like this, you will get it wrong. Yes, DJ. 3p5, again, one box will have one arrow pointing upwards. All right? Yes. That is Hunt's rule, that's right. We'll go to the back now. Let's go to the back. So you know what was very impressive today? He missed class last time and he went to Blackboard. And he knows. He did all the worksheet. He listened to all the videos. He said, this is easy stuff, Ms.Geeta. I'm like, no duh. All right? So, you know when kids don't understand stuff from Blackboard? It's when they don't do it. He did all the worksheets also. So he can really prepare. He's beyond me now. He's talking about Hunt's rule. Okay, now, so whenever they ask you to identify an element, are you listening? It's very important you count. It's very important you count up the number of electrons. Many a times there are a number of exceptions to writing electron configurations. Are you with me? So even though I know this is 4p2, it's not that big of a deal. 4p2 will be germanium. Is that right? I can very quickly look at the last one and say what element it is. Is that right? But since there are a number of exceptions to writing electron configurations, it's best you count up the electrons. So this is 2 plus 2, 4, plus 6, 10, 12, 18, 20, 30, 32, and now I know it's germanium. Does that make sense? Okay. Now, we're going to talk about the rules, and then we're going to come back. So guys, it's very interesting to learn the rules because we cannot even see an atom. The atom is so small. Is that right? And now we are talking about how the electrons are placed within that atom. If you think about it, it's like mind-boggling. Is that right? How the heck were they able to come up with these shapes and answers? So everything about an atom and its electrons is all mathematical. Do you understand? They all came from solving Schrodinger's wave equation. And so these rules that are formed are also a part of this solution. Does that make sense? So if you go to a standard chemistry textbook and read these rules, it'll be written in a language that is used to solve mathematical problems. But we are going to use everyday simple layman's language so that we understand the rules. Does that make sense? All right. Our first principle states that the lowest energy level must be filled first. Lowest energy level first. Aufbau means to build up, is the German word, is what I'm told. I don't know German, so anybody who knows the German language will perhaps relate to this more than I can. All right? So if I write an electron configuration as 1s2, I'm giving you an example. Are you with me? If I don't fill the 2s2 and I go to 2p and I say it's 2p3 and I ask you which rule has been violated, you should be able to say, well, the 2s was not filled in, so this violates Aufbau's rule. Are you understanding Aufbau's rule? Okay. Pauli's exclusion principle. If you read it in a textbook, it will say no 4 electrons can have the same 4 quantum numbers. But we are not going to look at it that way. Pauli's exclusion principle says, all right, says only 2 electrons in a box, which is also an orbital, is that right? And they must have opposite spins. Are we good? So why do we put only 2 in a 1s orbital? Because we are following Pauli's rule. We cannot put 3 electrons. Does that make sense? Or we cannot have them both pointing upwards or both pointing downwards. That's because we follow Pauli's exclusion principle. All right? Hund's rule applies to equal energy orbitals. Equal energy orbitals. Which are the equal energy orbitals? P, D, and F. You don't talk about Hund's rule for an s orbital because there is only one. It is equal to which other orbital? There is nothing like that for s. Is that right? Whereas when you draw P, you draw 3 boxes. Those 3 boxes are equal in energy. Is that right? And so what does Hund say? He says, Hund's rule says that an electron must be placed in each box before it is paired. Does that make sense? Do you understand? So for example, if I have 3 electrons in P, can I put them like that? Can I put 3 electrons like that in P? No. How should you place them? 1 in each before you pair them up. Why do we do that? Because we are obeying Hund's rule. Now Hund's rule is an everyday common sense rule because if you look at a p orbital like we saw before, the electrons repel. Is that right? It's like having 2 siblings that really don't get along with each other. Do you think they will be in the same room if they have another room in the house? They really don't like each other. Like electrons repel each other. Do you think they'll sit in the same region of space? No. Who says yes? Okay? Does that make sense? Okay. So let's do some of these rules and understand. What is being violated here? Which rule? Both of the arrows are upwards. This is Pauli's exclusion principle. Is that right? Pauli's rule is being violated in this picture. The 3s is not occupied completely. Which rule is being violated? Aufbau's. Off-Boss rule is being violated because the lower energy is not filled. Is that right? What is being violated here? Hund's rule is being violated because you need to put one in each box. Are we understanding? So let's go down. Let's look at this example. 1s2, 2s2, 2p6. What fills after 2p6? 3s2. Where is the 3s2? So this is off-Boss rule. So let's see. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What fills after 4s2? It should be 3d. So it should be 3d, not 4d. Again, this is off-Boss rule. Let's look at the next one. 1s2, 2s2, 2p6, 3s3. Can we place 3? So whose rule is that? Polly's. So this one, it says argon. If you look at argon, what follows argon? It should have been 4s2. Or the noble gas, if it's 3s2, what should the noble gas have been? It should have been neon. This isn't any rule, it's just that the noble gas configuration is written incorrectly. Does that make sense? Now let's look at the next one. Can you have a noble gas to be its own electron configuration? No, you should have started with argon and continued. Is that right? The last one is 1s2, 2s1. You didn't fill 2s before you jumped to 2p. What rule is that? Off-Boss rule. Are we understanding how the rules apply in various situations? Do we get this? Okay. The next thing we're going to do is we are going to talk about Bohr model, valence electrons and charges of the main group. Are we good?
Oh, yeah.
Okay.
No, we didn't get this. We did not get this.
You should have picked it up by the door. Owen? Yeah, it was.
Nothing that says this.
So guys, can you turn to the back of your warm-up? Honors electron configuration, extension note. We're going to do this. Oh, I didn't. That was a M11. Right, maybe I'm wrong. So let's go back. Where is your warm-up? This is your warm-up, right? So you should have this. Is that right? Is this the one you got over?
Yes, we have this.
Okay. All right. Very good. So now, can you all go to the back of your warm-up? Can we go to the back of the warm-up?
Yeah.
On the back of the warm-up, I want you to write the Bohr model. I don't think we have done Bohr model before, so we're going to do the Bohr model. And you're going to draw with me. Are you with me? All right. So hydrogen only has one electron. Is that right? So I'm going to draw, hydrogen is energy level 1. So it's one circle, that's the nucleus, and there's one electron in hydrogen. Is that right? Helium is a noble gas. Are we in helium? Helium also is in energy level 1, and helium has how many electrons? 2. And that is the maximum number of electrons that can go in the first energy level. Is that right? After helium comes the second energy level. And what is the first element at the second energy level? It is lithium. Lithium has 2 energy levels. 1, 2. Are you with me? The center is the nucleus. Is that right? How many maximum electrons can go into the first energy level? 2. Lithium has a total of 3 electrons. So how many electrons are in the outer ring? 1. After lithium comes beryllium. Beryllium is also in energy level 2. So we're going to draw two circles. This is lithium, this is beryllium. And beryllium has a total of 4 electrons. How many will go into the first ring? 2. And then it has 2 in the outer ring. Are you with me? After beryllium, I'm going to jump to boron. All right? Boron is also in the second energy level, but boron has 5 electrons. So how many in the outer energy level? 3. All right? I'm going to jump and I'm going to go to fluorine. Are you with me? Fluorine is also in the second energy level. Fluorine has total 9 electrons. Is that right? 2 in the outermost. So if you subtract 2, how many will go in the outermost ring? 7. Is that right? 7 plus 2 is 9. After that, it is neon, and neon is also in the second ring. It's 2 rings because it's in the second energy level, 2 in the first, but now it is 10, so it's going to be 8 in the outermost ring. Is that right? I'm going to repeat this for sodium. Sodium is in energy level 3. So how many rings should I draw for sodium? 3 rings. All right? 1, 2, 3. How many maximum can go into the first ring? 2. How many maximum can go into the second ring? 8. So 2 plus 8 is 10. So how much is left for sodium? 1 more. So there's 1 in the outermost ring. Are you with me? So let's go to magnesium. Magnesium also has 3 rings. How many will go in the first? 2. How many will go in the second? 8. 2 plus 8 is 10. Magnesium has 12. So how many in the outermost circle? 2. Is that right? So I'm skipping across and I'm coming to aluminum. This is sodium. This is magnesium. I'm coming to aluminum. Aluminum has 3 rings. 2 in the first, 8 in the second. That makes it 10. So how many in the outermost? 3.
How many can fit in the outer ring?
Well, after 8, you have to jump to the next ring.
Oh, so just 8.
Only in the first energy level.
Only the first energy level.
All right? Now let's come to, yes.
Why did you draw 2 next to each other and the one above but only 1?
So that's the maximum that can go in. Is that right? So then you cannot put more than 2 in the first energy level and you can show them as pairs. Outer ring, you generally, so this is the loose dot structure notations. In the outer ring, you put 1, 12 o'clock, 3 o'clock.
Why is that one not 2 next to each other?
That's just so that they are paired. In this case, this is not paired.
Why is the level 3?
So level 3, you first start putting like that, and then you start pairing it. After that, you pair it with all 4 eventually. So if I do aluminum, let's do let's do silicon or phosphorus. Let's do phosphorus in between. Phosphorus has 3 rings. Is that right? Phosphorus will have 3 rings. Are you with me? So phosphorus will have 2 in the first. How many in the second? 8. So 2 plus 8 is 10. What is phosphorus' number of electrons? 15. So it's going to be 1, 2, 3, 4, 5. Owen, did you watch me do that? That's how you do it. So if you take chlorine is going to be what? 3 again. Is that right? And chlorine will have 2 in the first, 8 in the second, How many in the third? 7. Is that right? After chlorine, we are coming to neon, and neon will be 3 circles.
Oh.
Is that right? Well, actually not neon, I lied, that's argon. And argon has 18, so 2, 4, 6, 8, 10. That's going to be 8. Are we good? I see a couple of hands going up, and so I'm going to answer questions now. Yes, Abdul.
Can you do one like radium?
We are not going to do radium. We are not going to do that right now. We're going to follow patterns that I have.
Radium has.
Can't keep drawing it. All right, Tanaya.
Why would it be radium? Bro, it's only 85.
So
Like 85.
why?
Shut up.
Why? The question is like this. Okay, if you're interested in the why of it, I'll explain that to you. At the first energy level, it's only 1s2. So what's the maximum number of electrons that can go in? 2. At the second energy level, it's 2s2, 2p6. What is the maximum number of electrons that can go in? 8. But at the third energy level, we're jumping a little ahead of ourselves, but let me explain it. All right? At the third energy level, when you draw your periodic table, are you with me? You fill the 4s2 and then you fill the 3d. Yes or no? So you have the 3s2, the 3p6, there is the 3d, but the 3d doesn't fill in before the 4s. Yes or no? So, before I go to explain why it's only 8 on the outer shell, I'll come back to that in a little bit. I want you to see a pattern. Are you seeing a pattern? How many electrons are there in the outermost shell? 1. If it's group 1. How many electrons are there in the outermost shell if it is group 2? 2. How many electrons are there in the outermost shell? Remember, we are skipping the D block. Are you with me? I skipped the D block altogether, and now I'm in the P block. Did you notice that boron and aluminum are in the P block? So that's group 13. Yes or no? So how many electrons are there? 3. Is that right? So if I go down to group 17, which is fluorine and chlorine, how many valence electrons are there? How many electrons in the outermost shell? 7. What is it for the last one? Ignore helium. What is it for the last one? 8. Is that right? Do you get this pattern? I'll come back to why it's only 8 in a little bit. We're going to go back and take some notes. And then we'll come back to this. Okay. So you need to know the term valence electrons. Valence electrons are electrons on the outermost energy level. Outermost energy level. Are you with me?
Yeah.
They are just the s and the p orbitals. They are just the s and the p orbitals. The maximum number of valence electrons, what was the maximum that we saw? 8. The maximum number of valence electrons is 8. Noble gases tend to be stable and unreactive because they have how many valence electrons? 8 valence electrons. Now, how do atoms form ions? Atoms form ions by adding or removing electrons in order to mimic noble gases. They do not become noble gases because the number of protons has not changed. This is called the octet rule. Having 8 to become stable is called the Octet rule. And we just drew the Bohr models. We didn't do it for homework. Now, we're going to write the electron configuration of hydrogen. Hydrogen is what? 1s, 1. Lithium is 1s2, 2s, 1. Sodium is 1s2, 2s2, 2p6, 3s1. Are we good? So now, this is the highest energy level in each one of these orbital notation. Is that right? Or electron configurations. How many valence electrons do they all have? 1. So, it's either 1s2, it's either 1s1 or 2s1 or 3s1. Is that right? So what do you think it will be for potassium? 4s1. So we can say in general it is ns1. Can I say that? Where n stands for the energy level. Whether it's 1, 2, 3, 4, etc. Do we understand this? So now these elements in group 1 have only 1 in their outermost energy level. Is that correct? When do elements become stable? When they have how many in their outermost shell? 8. Now tell me, will it be easier for this group to lose 1 or gain 7? So if they lose this 1 electron, this whole shell disappears. Are you with me? So what is on the inside shell now? 8. Does that make sense?
Yeah.
So elements in group 1 will lose how many valence electrons in order to become a stable ion. Therefore, if they lose 1, what is their charge? Positive 1. So, sodium looks like this. Sodium is the 3rd energy level. Is that right? So, sodium has 2 in the first, 8 in the second, and 1 in the outermost. This is sodium. When it becomes Na+, what happens? It becomes this. Yes or no? It loses the outermost shell and becomes 8. Does it make sense?
Yeah.
All right. Can we move on to the next page? Yes. Huh? The 3 is the energy level, the period number. Period number is 3. So how many circles will you draw? 3. Let's move on. Elements in group 2, beryllium, magnesium, have how many valence electrons? 2. Would they like to lose or gain to get to 8? What would they like to do? Lose. This means they will form a +2. What will be the N notation? NS2. So let's draw magnesium. Magnesium has 3. That's 2. That's 1, 2, 3, 4, 5, 6, 7, 8. And there's 2 in the outermost. Is that right?
Yes.
But then when it becomes Mg+2, what does it look like? So that's just 2 circles now. Is that right?
Yes.
Now that's 2 in the first and 8 in the second. Are we good?
Yes.
So now let's do boron. What is the electron configuration for boron? 1s2, 2s2, 2p1. If you look at aluminum, it's 1s2, 2s2, 2p6, 3s2, 3p1. So what is the highest energy level? This is the highest energy level.
S2P1.
The S and the P together is the highest energy level. So how many electrons do they have? 3. There are 3 electrons, all right, in their outermost, which means they have 3 valence electrons. When they form an ion, would they like to lose or gain? Lose 3. So what is their charge? Plus 3. And what will be the N notation? NS2 NP1. Correct? Are we following along, Sienna?
Yes.
All right. So aluminum has 3 rings. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. That is aluminum. Is that right? Now aluminum is becoming aluminum plus 3. It's losing all 3. So what will that look like? Only 2 rings. Yes or no? So it's 1, 2, 3, 4, 5, 6, 7, 8. Is that right?
They all look like that.
So let's answer the next question. The electron configuration or the orbital diagram of Na plus, Mg plus 2 and aluminum are all the same. Does this look the same as that?
Yeah.
Does this aluminum look the same like Mg plus 2? All right. So then let's see. Are all the same? They look exactly like the electron configuration of which element? Like neon. Neon also has 8. Yes or no? Which is a noble gas. We say that these ions are isoelectronic, iso meaning the same, having to do with electrons. Whether it's neon, whether it's fluorine minus, whether it's sodium plus, whether it's magnesium plus 2, whether it's aluminum plus 3, they all have 10 electrons. Yes or no? Okay? So now we're going to write the electron configuration for fluorine. 1s2, 2s2, 2p5. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So what is the outermost energy level? What is the outermost energy level? 7. So they all have 7 valence electrons. So what is their N notation? NS2 NP5. What do group 17 elements want to do if they have 7 valence electrons? Gain. How many electrons? 1. If they gain 1, what is their charge? -1.
Wait, what?
They gain only 1, so it's going to be -1. All right? Compare. Let's do oxygen's electron configuration. 1s2, 2s2, 2p4 is oxygen. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. What is the maximum number of electrons they have in the outermost shell? They have 6 electrons, which means they have 6 valence electrons. The N notation will be NS2 NP4. Will they like to lose or gain? Gain. How many electrons? 2. What will their charge become? -2. So if you look at nitrogen and phosphorus, that is before oxygen, group 15, how many valence electrons will they have? 5. All right? And so their N notation will be NS2 NP3. Will they gain or lose? Gain how many? 3. What will that charge become? -3. So now we are in a Lewis dot diagram. Boron has how many outside electrons? Group 13. Group 13. How many electrons in the outermost shell?
3.
3. Are you looking at those little sticky notes? Can you see those sticky notes on top of the group number? So boron will have how many? 3. Sodium will have how many? 1. How about magnesium? 2. Sulfur is how much? 6. 1, 2, 3, 4, 5, 6. Are we good? Chlorine is how much? Chlorine is 7. 1, 2, 3, 4, 5, 6, 7. Are we good?
Yes.
So now let's fill in this box. All that we learned now can be summarized in this table. Is that right? What is the family name? Alkali metals. Alkali metals have how many valence electrons? 1. What is the N notation? NS1. Oxidation state, also the charge, they like to lose and become +1. Right? The next one is alkaline earth metals. How many valence electrons? 2. What is the notation? NS2. What charge will they make? +2. We don't learn a family name for group 13, but we know they have 3 valence electrons. It's going to be NS2 and P1. And they will make a charge of +3. Group 14 is 4 valence electrons. It will be NS2 and P2. Now 8, half of 8 is 4. So it will be a plus or a minus. The next is 15, which is 5. So it's NS2 and P3. They will have 5, so they will gain 3 more. -3, 6. So it's going to be NS2 and P4. And it's going to be what? -2. Group 17 is known as the halogens. It has 7 valence electrons. It's going to be NS2 and P5. And it will be what charge? -1. The last one is noble gases. They have 8 valence electrons. It's going to be NS2 and P6, and they do not form bonds. Do we understand this?
Yes.
Are we good thus far?
Yeah.
Okay, I'm going to stop this.
Hold on.